we just started to look at measurable spaces and measure spaces, and we said the measurable space just meant that you had a sigma field on a set X, and then I told you what a measure was, so that you could make a measure space by taking a set with a sigma field and a measure on it. So what was a measure? So here was our notion of a measure. And I'll just say a little bit more about this before we look at lots of examples. So I've already mentioned that we want the measure of the empty set to be 0, and you can't quite deduce that from the second axiom, though you almost can. What I mean was that if you weren't including the value infinity, then you can actually deduce the first axiom from the second. But what you don't want to allow is something that always takes a value plus infinity. If you take something that always takes a value plus infinity, it does satisfy the second one, but it wouldn't be what we want the measure to do. We do want the measure of the empty set to be 0. So that's why there's a slight extra there with condition 1. Okay, so how we describe this second condition? Describe this second condition as a countable additivity. That means if you've got countably many pairwise disjoint sets, and I'll just remind you what that means no pair of them meet. So this pairwise disjoint business, so for m and n in the natural numbers with m not equal to n, we have am intersection an equals empty set. That's the pairwise disjoint bit. And countable additivity means then that if you've got an infinite sequence of pairwise disjoint sets, then the measure of the disjoint union is exactly equal to the sum of the measures of the pieces. You can think that this is countably infinite unions. We'll look at finite unions in a moment. As usual, you can deduce the finite one from the infinite one, given the information we've got, that the measure of the empty set is 0. And a bit of notation that could be useful. You could set A to be the union from n equals 1 to infinity of an. And you can write A to be equal to the disjoint union from n equals 1 to infinity an. That dot in the middle you can write to help remind you that it's a disjoint union, which means you've got more information. So this union with a dot in the middle to remind you that the union is a disjoint union. And so we've got measure of A equals the measure of the disjoint union from n equals 1 to infinity an equals the sum from n equals 1 to infinity of mu of an Noting, of course, that all of the sets involved are in your sigma algebra F. And of course A as well. So the rules to be a measure are pretty simple. What's interesting is how much you can already deduce from that. And as a result, well, so being a measure is actually rather powerful. And this countable additivity is rather better than just finite additivity. And so it can be almost too much to hope for sometimes, but we'll see lots of situations where you can get it. So we don't have Lebesgue measure yet, but I've told you a little bit about it. The idea is that, in 2 dimensions, you want area of as many sets as possible, and at least you can do it for the Borel sets. And in 3 dimensions, you want to get volume for as many sets as possible, and at least you can do it for the Borel sets, and you can do it for a few more. In 1 dimension, which is where we're going to work mostly, you get a 1-dimensional version, which is going to do something to do with length, the total length of your set, and we'll get a measure that does the right thing on intervals, it'll do the right thing on unions of sequences of intervals, and in fact, that'll then go on and help you to decide what the total length you should assign to every Borel set is, which will be more than enough sets for us. They can go on to slightly more sets called the Lebesgue measurement sets. So that's why I say here we're going to define Lebesgue measure, which will be total length. It'll be on the Borel sets or the Lebesgue measurable sets. But just for now, the theory you need to develop that, I don't want to go into that here. I will be sketching how that works later without full details and referring you to my former notes from measuring integration if you want to get full details on the construction of the Lebesgue measure. I will give you a formula that's correct that will define what the Lebesgue measure is on all Borel sets, but some of the theory behind it I won't do in full detail. I'll leave it to you to read up on some of the extra details as a reading exercise. Okay, let's have a look at some easier measures then. Well, examples and non-examples. So note that if you say mu of E is equal to plus infinity for all E in F, satisfies 2 but fails 1. It does satisfy the rule for sums, because infinity plus infinity is infinity, but it fails 1. We don't include this as a measure. Now there's a useful one that works on all subsets of a set, on any set. So for any set X, take F to be P of X, the biggest possible sigma field. You can define counting measure. As follows. There's a little bit of redundancy in this one. Mu of the empty set should be 0. You need that. Mu of E equals infinity if E has infinitely many points. And otherwise, mu of E is the number of points in it. So that counting measure always works. I'll leave it as an exercise, prove that this is a measure. There are a few little minor details to check, but it's a standard example of a measure. You can quote this as a measure unless you're asked to prove it. So this is a standard example of a measure. So unless you're asked to prove it's a measure, you can assume it's a measure. But as an exercise, just in case you are asked someday, prove that counting measure is a measure. You can use it on the real line, all subsets of the real line if you want, but it's not very good because intervals are usually sets of infinite many points in. So it's not a very exciting measure because for most interesting sets you just pick up the value infinity, and so it doesn't help you very much. It is usually used not on uncountable sets but on countable sets. So it's one of the measures you'd expect to use on a countable set, like the natural numbers or Z. So we often use counting measure on N or Z or countable sets. It's not so useful on R. And when I say on N or Z, of course I mean defining, we're talking about the set of subsets of these things. So if you take a subset of natural numbers, then it's either finite or infinite. If it's infinite, it's still countably infinite. But the counting measure doesn't detect which kind of infinity. It just tells you whether it's finite or infinite, and if so, how many points in it. Oh, I said there was redundancy. Whoops. What's this redundancy? Well, the empty set is a finite set with number of points in it 0. So this first one about the empty set is actually a special case of the third one, which is, so that's when E is finite. Finitely many points, not bounded, finite. So that includes the empty set as a special case. But I thought I'd just be explicit about it, just to be clear. Right, what else have we got? I'll just give you a few more examples and constructions. You can multiply any measure by any non-negative extended real number and you'll still get a measure. And you can add them together. So for mu and mu measures on F, where F is a sigma field on X, on a set X, and alpha beta in the non-negative extended real numbers, you can define alpha mu plus beta mu, a new measure, alpha mu of E, sorry, the new measure what does it do? Exactly what you expect. Alpha mu plus beta nu, if you want to do what it does to E, you just combine them in the obvious way. That's for E in a sigma field. And this is then still a measure. There's a little subtlety in here. You remember there was a problem with the algebra of limits for sequences. So you might think there could be a problem with an algebra limit for series. But you may remember again that you were absolutely safe as long as you have monotone increasing sequences. And when you do a series of non-negative extended real numbers, that gives you a monotone increasing sequence of extended real numbers. So the problems all go away that we were worried about with the algebra of limits, and everything works as it should do here. So any constant multiple of a series of non-negative numbers is fine, and everything works as it ought to. In particular, suppose you take the power set of x, you can do infinity times counting measure. Is a measure. It's a rather boring measure. Defined on all subsets of x, infinity times counting measure has a rather easy formula. What do you get as your measure, infinity times counting measure?
0 is empty and then infinity otherwise.
That's right. And this is the biggest possible measure you can have. Okay? It has to be 0 at the empty set, otherwise, obviously, infinity is the biggest it can be. This is the biggest possible measure on any sigma field, in particular on the power set as well. Finally, I'm going to tell you about some point mass measures. And again, I'll do it on any set and on the whole power set. So again, take F to be the whole power set, but you could do it on any other sigma field as well. And let X be a point in X. Define delta X. Well, I say it's going to non-negative extended real numbers, but actually it only takes the values 0 and 1. So it's 0 if X is not in E, and 1 if X is in E. Now, does that look familiar, that formula, and what does it remind you of? Does that remind you of anything?
What we would call the delta function.
Okay, so first of all, it is exactly going to correspond to the delta function. In fact, integrating against this measure, if you do measure and integration, gives you exactly the same results as integrating against the delta function. That's what this measure is designed to do. So this measure actually, if you like, you can think of this measure as being what the delta function really is. the delta function isn't really a function. It's, you can either regard the delta function as a generalized function, you can think of it as a measure, or as a distribution, even more generally than that. If you're regarding it as a measure, this is the measure you want for the delta function, which gives you evaluated x. But what I really wanted to ask about was this formula here. Forget about the notation delta x for the moment. This value here, naught if x is in E and 1 if x is, naught if x is not in E and 1 if x is in E, should look familiar. It should look like something else. I mean, I just wanted to say, what does it look like and what's the difference?
The characteristic function of E.
That's right. This looks like the characteristic function of E. And so, in fact, this is equal to the characteristic function of E evaluated at x. But what's the difference?
One maps from the power set to the 0, 1, and one maps from the set to 0, 1.
That's right. So in other words, one of these is a function of E, and the other one is a function of x. So the one we're looking at the moment is a function of E, so it's a function from the power set. The other one is a function of little x, and that's from x. So they're not the same, the characteristic function and the point mass measure, because one is a function of little x and one is a function of the set E. Different variable, completely different kind of variable. So E is the variable here. And here x is the variable here. And then, of course, you can combine them. I've given you methods for combining measures together, so you can combine and make finite combinations of point mass measures and things like that. And there's a whole theory about approximating measures using other measures and so on. We won't go into that in detail here. I think what I'll do, that will do for this introductory section on measurable spaces and measure spaces. But are there any questions on what we said so far? If not, we'll finish this section, and I'll tell you some of the standard properties of measures. And let's just fix that word variable. Okay, so we'll stop that recording there.